Good.
Okay, so today we'll try to, again, I guess, a bootstrap, I hope more focused discussion on light client. And so let me just share the screen. And okay, so I was trying to more or less summarize where we stand. There have been several issues and several concerns distributed more or less across the repo. And so I tried to also we were trying to figure out something with Josef recently on how to securely update validator sets. And so I kind of tried to consolidate all this work more or less and put it in a form that we can then start really working on it and making some decision basically. I will try to walk you through some of the concerns and my current thinking about the stuff and some proposals also you will see. But essentially, all this is very much, I think, for a lot of stuff, my thinking on the stuff. And so feel free to interrupt and challenge me like on the way. So light client, just to give a one sentence overview, it's a process that connects to Tendermint full node or a set of hopefully full nodes, and then you try to verify application data using Merkle proofs. And so this high level description, there are a lot of implications which hopefully some of them will try to cover today. So the first thing is that essentially when the client, light client, connects to a system, it needs to figure out where it stands with respect to the concept known as unbonding period. Because so there are essentially two very important concerns about light client. The first one is a validator set, because knowing validator set give you a possibility to verify headers, and then through headers also the root hash and then the Merkle proofs of the application state. And in the proof of stake systems, including like Cosmos Hub, validators are accountable only during or slashable during something we call unbonding period, which is normally order of days. Like in Cosmos Hub, it's 3 weeks. And so outside the unbonding period, we don't have a mean to punish validators. And so that's why we are essentially only secured during unbonding period. And so unbonding period is a period from the point validators withdraw their stake until the stake become liquid, or until they are essentially, from our point of view, they are gone. So we cannot do anything about that. And also very important notion which is related to unbonding period is a concept of BFT time. And so Tendermint provides a Byzantine fault-tolerant deterministic source of time, which is currently implemented by a weighted median, and it guarantees that the time is monotonically increasing, and also that if our assumption on the maximum number of fault processes holds, we have the time being between the wall time of correct validators. So if you assume that correct validators are their clock, their wall time is not wrong, then the BFT time should give us a guarantee that it's more or less close to the wall time. And so the unbonding period is also defined with respect to this BFT time. That's why I mentioned this. So now the first thing which we need to figure out is how the client, when it try to connect to a system and establish some root of trust, how it can figure out whether he's within the unbonding period essentially or not. Because this is more or less the first thing we kind of need to figure out. and the unbonding, so this unbonding is essentially related with the unbonding period, more or less. And unbonding period right now is expressed, as I mentioned, in a real time. And so this is kind of the first thing which I was thinking about, because, time in distributed system is very hard. And so I was wondering, the first thing which I'm kind of always trying to do is avoid using time, because dealing with time is super error prone and tricky. And it turns out that from the point of view of light client, unbonding period needs to be related with the real time. Otherwise, for example, unbonding period can be defined with respect to logical time, like number of heights. In that case, when the client connects to a system, he doesn't have any clue, how far he is from the end of the unbonding period of the validator set he's trying to trust. And therefore, it seems that and the reason for this is that we don't know where the chain is, essentially what is the top of the chain. We don't have a reliable way of doing this in asynchronous system. So if we have some notion of time which is close to the client wall time, then it seems that we can reason about how fresh validator set is, and then whether we are secure or not. So I want to stop here and more or less to see if there are questions about this, because it's somehow this is more or less the base of a lot of stuff we are supposed to discuss today.
So I had a question, and it came from a discussion about this that I had with Sunny for the all in bit side, and that is so there must be something. We know that we can trust the what did you call it, BFT time? Is that what you referred to it as?
Exactly. So the BFT time is source of all computation we are doing.
Because and we know we can trust it because it's in the block, and the block got voted on, so then enough nodes have said this is indeed the time. And then we also know which, at that point we also know, because we have some list of transactions which we also trust, which include this validator has this much stake. Is that also true?
Yeah.
So so the fact that a validator has stake, right, is some kind of computation of all the transactions that have happened up until that time, and that we know that we trust that, right? Am I understanding that correctly, or am I missing something?
So you're talking from the light client perspective or in general?
From the light client perspective. So I'm a node, I know nothing. So I'm looking at a bunch of transactions. I'm trying to figure out two things. What time is it? And that how much stake does someone have bonded?
Not quite. It's not true that when you start up, you know nothing, because you have to come to the table with some piece of information you got from social consensus. So you have to be a light client. You're not, your initial state isn't empty. It's a validator set and a height that you trust because you received it from some trusted source.
Okay,
and
so
you're taking for granted an initial validator set.
Yeah. Okay, and that comes from GitHub or something.
From GitHub or from your local 7-Eleven or wherever you get your source of truth from, and then the question is, okay, am I still within the unbonding period from the time that I received that initial state, right?
Yep. So you really have to compute to find out how much the bonding period, or the exposure of a validator and the blocks. I have to apply a bunch of transactions. Is that true?
No, you shouldn't. Basically, you say, okay, so you go to 7-Eleven, you ask the nice cashier there, for a recent block height and a validator set that they trust for their, gas transactions or whatever. And then you take that, you go back home, you initialize your light client with the height, the time, and the validator set. And then you look at your watch and you say, okay, given, this, it's, it's 7 p.m. on Thursday, and the thing that the 7-Eleven guy gave you is from 2 p.m. on Tuesday.
Okay.
And so now you say, okay, am I still within, according to my local clock, am I still within the unbonding period from the time that this trusted validator set came from, which was 2 p.m. Tuesday. You say, okay, 2 p.m. on Tuesday, today at 7 p.m. Thursday, that's, 50 hours or something. So I have 3 weeks, so I'm still okay. So now I can start from 2 p.m. on Tuesday and securely sync using the Lite client protocol to the latest state at whatever it is today, and then keep going from there.
So it's actually not like within or without. It's like it's the upper bound. So we know that at most 21 days can pass since we're given any piece of data that has been validated through 7-Eleven or through GitHub or whatever.
Right.
Yeah, essentially, yeah, we simplify this reasoning a bit. We just, if you know the header we trust, if you know validator set for a given height, essentially, this give us possibility to verify the header, and then knowing the header give us possibility about the current time at which validator was for sure in power. Because like asking Tendermint to tell you what is the validator set which sign given block means that they are in power, that they are not removed, they haven't withdrawn their stake.
Okay.
And so we don't need to track, at the transactional level when they withdraw their stake. So this is implicit from the fact that you ask what is the current validator set. And we also have something which is called next validator set, but essentially this is the granularity at which we are tracking this. But more or less, like the two very important pieces of information are what is the validator set we trust, and initially this is what, as Bucky said, like what is given to us from the from external world where we really trust something. And from this information, we more or less then try to develop our trust in a system in a following period.
Oh yeah.
So
okay.
the first. Okay.
This is super helpful. And just as an initial comment, like the chain of trust that led to the assumptions that describe the security model in the document that you're showing us, it'd be cool if that was sort of present. So like.
Yeah, I think that. I think that. Mm-hmm.
Okay.
Normally, so we have this. So there is this Lite client initialization where we exactly talk about this. But more or less, what we have here is my try to just define these, let's say, terms which we need to use to realize the stuff.
Okay, I'm sorry for
and yeah, you see here that more or less I call these requirements from Tendermint and proof of stake. Because Lite client have some assumption about how Tendermint and proof of stake modules operate, and then so we kind of need to define this thing. And so the most important things are this concept of unbonding period, and the second is the relation that the BFT time needs to be close to the real time, to the wall time. Otherwise, it's not obvious to me how you can figure out when you connect to a system whether you are still during the unbonding period or not.
The other thing I want to point out is it's just a little bit pedantic, but based on your opening line there about in this document, we describe mechanisms so that the Lite client has the same level of security as a full node. It's actually not going to be the same level of security because this kind of goes back to the question Sean was asking. The goal and the idea is that a Lite client never actually has to execute transactions. And so really the difference in the security model is that the Lite client is trusting that the executions are happening correctly and that it's not being, it's really a question of equivocation. So it has the same security with respect to equivocation, but not necessarily with respect to validity of transaction execution, right? Because it's still possible that the validators will, execute a block invalidly, and they don't necessarily equivocate in the sense of like double signing or something that could cause a fork, but the execution doesn't follow the rules, and the Lite client would never be any of the wiser. So unless it's actually fully executing the blocks, it's not going to have the same security as a full node. So there's just
you're right. All right. That's a very good point. Yeah. That's a very good point. So essentially, like to more or less define a base ground from Tendermint, we expect that Tendermint supports Byzantine fault tolerant source of time and this time should be close to the real time. And I define here some bound, which more or less should capture the drift between the BFT time and the real time. And
I would like to add something, because it's also related to what we expect from Tendermint. It's the observation that sort of the assumption of who we trust, there is cyclic dependency to the consensus algorithm. Because the consensus algorithm is based on the assumptions that the validator set has less than a third of faulty voting power. But then we create new blocks, which means that we're going to compute the new validator sets, which then basically for the future sets out who we trust. And this is sort of, this cyclic dependency sort of is then, how do you say that, resolved by referring to time. I think that actually really having this time explicit and precise is something which is very important also from that viewpoint, because otherwise this cyclic dependency becomes not so clear.
Sorry, can you clarify what the cyclic dependency is again?
Well, you assume the point is that you prove the consensus algorithm correct on the assumption that the voting power of the validators, of faulty validators, is less than a third. But you're deciding actually on the validators for the next block, which means that sort of the outcome of the consensus for this block decides on your fault assumption for the next block.
Right. Oh, I see.
Yeah, so we if we trust, so the trust relation goes always upward, essentially. Like if you trust validator set at height h, you also trust what they sign for the height h plus 1. So that, and they could sign the complete change of validator set. So I think that, like, maybe what Joseph want to say is that essentially the time captured this relation, that, you know, like the trust always go with time, like it doesn't go backward. The trust cannot go backward. The fact that I trust height h does not mean that I also trust height h plus 1, h minus 1, and those guys who sign height h. But we'll come also to this after. So one more thing I want to mention here, that there is also one additional implicit assumption, which at least in the current version of the complete stack, and this is the fact that during unbonding period, we are always making progress at the Tendermint level. Like if you would not have blocks during unbonding period, then essentially you would not be secure, because like the security of which is covered by unbonding period implicitly also have part which is not seen, and this is that if you detect fork or if you detect any misbehavior, you will have time to submit this proof of misbehavior and to also execute it by the Tendermint, so that the bad guys are punished. And so that's why, like, from the point of view, when you withdraw your stake, we assume that there is some period of time during which we have time to maybe catch some bad behavior and then have time to execute and process it. And this is something where I'm not sure that that this is like the best idea, is defining unbonding period with respect to only time. And there have already been some discussion also on the GitHub whether it makes sense to have this as a hybrid, and which would be basically a mix of time and heights, consensus heights or block heights. And for me, this seems more reasonable. Like that with heights you want to approximate the time period, and that you are essentially in a case where system is not making progress, you are still secure. That it cannot happen, that, you know, just for the fact, although it's very unrealistic, but I just feel weird that, you know, like if for any reason chain halt, we are less and less secure during that period. this seems somehow wrong.
So I agree that this would be a desirable assumption. The question is, can you figure out, I mean, can you exploit, maybe in an asynchronous system, can you figure out that the chain halted and therefore you're sort of in the assumption which is based on the heights? But this is, I mean, it's a very theoretical discussion, but it just makes the assumptions clear.
No, the thing is that, like, essentially, if the system halted and you express unbonding period as a number of heights, you just have a higher chance of processing still, some proof of misbehavior. And especially if you define unbonding period in number of blocks as a function of the block execution time in the previous, X blocks.
Okay.
This might give you a possibility. So in asynchronous system, it seems that having any sort of synchronous assumption it seems like fundamentally wrong. But as we are talking here about very long period, and also the fact that we have the social consensus which can come into play, I think that this can be seen as a reasonable thing. But I think that we are more secure if we have a hybrid wall time and logical time as part of unbonding period. Although what client would use would essentially be just a wall time, because you as a client, you don't have a way to measure the time with respect to the logical time. It's just that you would essentially be covered by the logical time, because logical time should always be bigger than the unbonding period defined in terms of wall time.
Okay, that makes sense. Yeah. Good.
Okay. So this is like these are sort of the basics, and then now we can talk about operation of the light clients. And so as Bucky said, like the first thing we need to obtain if you want to start to initialize the light client is to obtain a trusted socially verified validator set hash. And this is what is called, if I'm not wrong, subjective validity, and this is a part of the basically security model of proof of stake blockchains. And so what we assume that the initialization procedure receives as input is some height at which there is a given trusted validator set for which we have a hash, essentially. And if we have this information, then we can call validators method on Tendermint RPC to obtain the validator set for a given block height. And if we have this, then we can check whether the hash of the validator set corresponds to what we have as a trusted validator set. And of course, if this fails, then we haven't initialized light client correctly, so we need to do something else. In case the hash corresponds to the validator set we obtain, then we need to next thing is we need to check if the header at height h is correctly signed by the obtained validator set. And to do this, this is something which I'm kind of, let me explain this, but this is not necessarily needed, because if you trust validator set at height h, you can just download the validators and check the hash. And this is sufficient for you to more or less initialize the light client. So this would essentially be probably enough that you say, okay, I trust this hash at height h, so just give me the validator set which corresponds to that hash, and I'm fine. But what I did here is more or less one step ahead, and this is like checking also the commit which corresponds to that block height h, and checking that commit is indeed signed by more than 2/3 of the what I consider as the trusted validator set. And the benefit of this is that we also verify the header of the block at height h, and as part of the header we have time, which actually then give us possibility to check whether we are within the unbonding period or not. And the second thing is that it gives us also the next validator set hash. So as part of the header, we have a hash of the current validator set that signed the block H, but we also have a next validator set hash. And if we have a trust in validator set at block H, we also then trust the next validator set, which is signed by the current validator set. And regarding the time, as I mentioned, we can essentially check whether the header time or whether at a point in time we are calling this initialization procedure, the current time plus unbonding period is smaller than our current time minus the drift bound of BFT time.
Wait.
There are some questions regarding this.
Shouldn't it be greater than?
This is the formula for, so the now minus BFT time drift bound should be smaller. Yeah, you're right. It's the other way around. Yeah, I think I expressed it. The problem is that I expressed it into the code as a negative condition, and so maybe here it's wrong.
Right.
Are you pulling the unbonding period from the block?
What do you mean?
So
Like,
for what we obtain from the block.
No, the unbonding period is constant. It's 3 weeks.
Go ahead.
Oh, is it not a parameter in the chain? Or is it
Well, it's fixed at Genesis.
okay.
I mean, I guess in a world where it could change, then it would be part of the initialization criteria that you have to get it as part of the trusted thing. This is actually, it seems in some sense what you're really trying to get, to initialize your Lite client is the Tendermint state object, which contains roughly, the latest height, the latest time, the current validator set, the next validator set, and the consensus params, which I believe includes the unbonding period. It includes roughly the max age, but right now it's only it's in terms of height and Tendermint, and because we have to make changes to the BFT time to.
Okay,
Very quick question. The drift bound, that's something that is also a constant. It's the same case and it's a small number, right?
Yeah, I mean,
yes.
It's kind of an abstraction. It's basically trying to say that the protocol is going to guarantee that whatever the BFT time is in the Tendermint header is within some drift bound from anyone in the world's local clock, or in this case, the Lite client's local clock. So if you have a local clock and it's roughly correct, then it's guaranteed to be within BFT drift bound from the BFT time in the blockchain. So this is like an assertion or an assumption that, it's hard to know exactly what that value should be. So we'll have to err on the side of conservative caution, but again, time is tricky. So
I mean, the concept is clear, but it's not that we are adapting based on network conditions, the bound. The bound is defined at the very beginning and that's fixed forever.
I think so.
Okay.
Yeah, essentially, so what is assumed here is some sort of NTP protocol where all the nodes in a system have their clock synchronized, and then we have this way to compute the time in a Byzantine fault tolerant way, the BFT time, and so that it's essentially doesn't go beyond some defined drift.
Right. Yeah.
But this part is, as I said, this is something which goes beyond the Lite client itself, and I'm not really sure what would be the best way to do things there. I'm changing my mind every day, but I just needed to more or less define some notion here so we can define what Lite client requirements are. But now, how we would really support this, or how we can really satisfy this constraint on BFT time, this is more or less it's a different question.
Yeah.
Okay. And so to be more precise, so now, so what we have, where we stand essentially. So we have this trusted validator set hash for a given height. So we download the corresponding validator set, we verify whether the hash is fine, and then we download the corresponding commit for that block. So we can verify the header. And if we do this, then we have like full information in the header is covered by the validator set we trust. So we can also trust the header. And so part of the information, like important information in the header from the point of view of light client are header time. So we can check whether we are within unbonding period. And the second one is the next validator set hash, because the next validator set hash are actually giving us immediately also trust in the next validator set, and not just the current one. So we kind of we have immediately also trust in the next validator set, and together with also the current one. And now here, like to be more secure, what I'm sort of proposing here is that from the point of view of light client, we don't operate within unbonding period, but instead we use a smaller time period, which is a fraction of the unbonding period. And I'm referring to this time period here as a light client certificate period. So you can think about this, that essentially if I'm able to initialize my light client with a trusted validator set for given height, then I'm essentially receiving a certification from the let's say Tendermint point of view that I am fine to operate within using light client in a context of that validator set for some period of time, which is smaller than unbonding period. And the reason why it should be smaller than unbonding period is the fact that that from the light client point of view, you also want a guarantee that in case you detect some misbehavior, you have enough time to submit this misbehavior to Tendermint, and the Tendermint has enough time to process this. Because if this is not the case, then essentially we don't have a strong incentive for full nodes to behave correctly, essentially, or not full nodes, for the validators. Because you can essentially, from the light client point of view, if your node to which he's talking is essentially, this node can essentially eclipse the light client and send them some forked information which does not correspond to the main chain. And if this happens just before unbonding period, you don't have enough time to submit this and to execute them, and you are essentially not secure at all.
Is that clear to everyone, the distinction between the light client certificate period and the unbonding period?
I think the point here is that what Zarko makes explicit is the property of the unbonding period, that you are always, that it's long enough that you can detect the behavior and slash it. And somehow, I guess the 3 weeks is just a way of saying, okay, it's always going to be quick enough for its assumption. And here, since you want to make this explicit, that this is possible, you have to say, look, I have to, can only use this information until then, because otherwise I will not be able to detect in the period, right?
Yeah, the difference here is that if you think from the validator point of view or full node point of view, at a point some validator withdraw, at the main chain he cannot do anything because he doesn't have possibility to sign protocol messages. But this doesn't prevent a validator, which is not anymore in power, to sign messages to create a fork, essentially, and then to try to convince some client about this fork. So although this is not happening on the main chain, this can happen at the kind of light client or tomorrow IBC context. And therefore, unbonding period give us security at the main chain level. Because after you withdraw, we have 3 weeks or whatever is the duration of unbonding period to detect any misbehavior on the main chain. But if you are, if you consider this from the light client point of view, then you can essentially be tricked by at any point in time, including just before unbonding period ends, and then you would not be able to submit the proof of misbehavior and protect yourself essentially. You'll not be able to submit and execute this proof of misbehavior or evidence transaction at the main chain. And this is something which is kind of, it's a tricky because we are essentially introducing some kind of synchronous assumption in the system. We more or less make assumption here that if during the light client certificate period, client is able to detect some misbehavior, for example, you detect a fork or equivocation, then it will have enough time to submit this through the network, and the network will execute it before unbonding period is over. And here I was assuming that these are essentially very long time periods, normally expressed in days, and although we don't have any guarantee right now at the Tendermint level about sort of that this transaction will not be filtered out by nodes on the way. As we talk about days, we can imagine again some kind of social aspect here, that if you try to submit evidence and no one is processing this, you can try to raise this at a sort of social level or talk directly with validators to process this this very important transaction. And I was even imagining that validators can offer as part of their service some kind of hotline where you can submit evidence of misbehavior, so that we can indeed operate within this trust period essentially. And then have a strong incentives for validators not to misbehave to light client, because they have a way to sort of share this with the world in a reasonable time frame, and then they can be punished. So we still sort of assume here that that this evidence will be processed on time, and this is again something which goes back to this idea of unbonding period, which is not expressed just in terms of time but also the heights. So it's more or less the same thing, we just want to sort of extend this period as much as possible in case of some kind of attack, that we increase the chance of evidence being processed by Tendermint. So do you have some questions regarding the light client certificate or all the stuff mentioned right up to this point? So just to more or less to formalize this thing, I mentioned a little bit of pseudocode, where essentially from the Tendermint RPC, we assume that there are two functions being exposed, which we have right now. The first one is to obtain validators for the given height, and the second one is to obtain for a given height sign header, which is a header plus the last commit, which covered that header, which actually comes from the next block. And you can see here essentially how the return values look like. And then I assume that the light client manages the following state, and here actually it's a mistake. There is only val set and val set hash and not next val set. So please ignore this. And now we have initialization procedure, which received height and validator set hash with trust, and it actually used to initialize the light client state. So by doing more or less what we just mentioned, that it gets the validators for the given height, check whether hash is fine, then it obtained the commit, check whether the actually check if the time is within light client certificate period, then it's check whether voting power of the validator set as part of the commit is greater than 2/3 of total voting power. And if at this point we can then obtain also the next validator set, because this is what we have in a header, and we can check when. Essentially, we do this by calling validators for the height +1, because we don't have right now a way to call, if I'm not wrong, at the Tendermint RPC level to say what is the next validator set. So this is the how more or less we were doing this. And at this point in time, we can set a trust in the next validator set for which is initialized by the given height, and the initialization happen at this header time. So this more or less tell us, or this can be used as a base to compute how far we are covered by light client certificate period.
So basically, this lets us jump to the next validator set actually right away. So even
this is something I was kind of I was thinking like a good part of today, like what we do with this next file set and current file set, because essentially if I have a trust in validator set at height h, I get for free also next validator set.
Yeah.
And so I essentially, and the question is, when the next file set is initialized, and it's actually initialized by the current validator set once it's signed, the hash of them. So this is something which was kind of not obvious for me when I started working on this. But after you initialize,
we trust the next validator set at the BFT time of the current block, or when we of the BFT time of the next block that sort of signed the current block.
So here the val set time is set to the time of the current block. So if you are at block H, you obtain the commit and header for block H, and then this defines both the current validator set as sort of in power, but also next validator set. So the time when you essentially, at least this is my understanding, that the time, so it's not next height. It's really like, although the validator set will be in power starting from the next block, once the next file set hash is part of the header, we can assume that from the trust relation point of view, that it's initialized, it's installed.
Yeah, I think that's a definition question. You just have to define the trust model. You are free to choose whenever you start trusting, and you can just do it right away.
Yeah, exactly. And I think it's also kind of more conservative if we always, if we start measuring time earlier and, ending the period also earlier, so that we have.
Yes. Thanks.
Okay. And so this is like how we can initialize the light client. And then now a very important thing to understand is that what you can now do once you initialize the light client. And the first thing is that within the light client certificate period, you can query the application state about the current height. As you have a trust, you essentially initialize the trust for height h, then you can ask the application state whatever you want about the state of the application at height h. But if you want to ask something about the follow-up state, you need to forward your trust in a system, because validator set might change potentially every height. And the same thing is also what I mentioned for like some information about application state for smaller heights. Like if you're interested in a height -10, then this is not helping you, because we don't have a trust relation for the past, only for the future. And so if you want to figure out what was the application state 10 heights ago, you would need to initialize the light client with a trusted piece of information for a smaller heights. So for the past, you essentially, see, this is my understanding. So you need essentially to kind of go back and redo the work. If you want to check something from the future heights, then we can do this, and this is more or less the procedure for doing this, which more or less, given the light line state, so given a trust in particular validator set at a given height, there is this is a procedure how we can develop or how we can progress our trust in a system for some follow-up height.
I thought we could go backwards because of the parent hash and the commit hash and everything.
Maybe I'm wrong here, but the problem is the fact that I have a trust in a validator set, and so you can reach validator set at height h by following many branches, and how to know which one is correct.
Because you have the last hash. Like if your validator signed a block that includes a pointer to the previous block, so you can just follow the pointer.
This is true.
So this is one of the key, I guess, examples of why having having it be a blockchain data structure is actually valuable. Because of the integrity guarantees it gives to the light client that you can actually follow the chain backwards.
Ethan, could you explain again how you can go backwards? I didn't get that.
So just because, if I have a trusted validator set for height h, and they signed height h, and so I know the header at height h, and I trust it. Well, the header at height h includes the hash for the block at h-1. That's part of the definition of the blockchain is that each block points to the previous block with a cryptographic commitment. And so if I trust the validators at height h and I have a trusted header at height h, well, then I know for sure that I know what the block is at h-1 because the validators I trust signed the hash of block h-1.
Okay.
And so now I can go to h-1, and then I don't have to keep verifying signatures. I can just follow the cryptographic commitments, assuming I trust the hash function. Because no one can forge a block that's going to match the hash. So I basically have a guarantee without even, it's a light client protocol because you don't even have to verify signatures going backwards. You just check hashes. I mean, I think I don't see why that would be wrong on first glance. I haven't thought about it too much, but
yeah, this is true. Yeah, I forgot about this thing. Okay, so about at least going.
Sorry, does that make sense to you?
Yes, I understand. Yeah, I'm just storing it in my brain. It's all good. Thanks.
Cool.
But
okay.
But now the question is, because maybe I also misunderstood this also for going in the future, can we use the same reasoning to go also in the future? So we can just follow?
No, of course not, because you don't know what the next block is.
Mm-hmm.
And you could have forks, right? So you could have the issue is if I trust block H has a single pointer to h-1. And so assuming I trust the security of the hash function, no one can forge h-1. So I know definitively what it is, and I can transitively follow that backwards. But going forward, anyone can make, we can make 1,000 new blocks that contain the hash of block H at height h+1. And so I don't know which of those are legitimate. So the reasoning works easily going back because of the, unforgeability of the hash function. But going forward, anyone can create a new block that includes the hash of my block. And so we can't just do this going forward because we have to deal with equivocation and forking.
Yeah, good. So thanks for clarifying this. So so if you want to go to update our trust in a system going forward, then essentially, so what I wrote here is the sequential specification. So the one where essentially we don't do skips, but we go height by height essentially. And it relies on the fact that we are always writing in a current block, we write the next validator set hash, which will be used as a validator for the next block. And so the procedure is kind of simple. So first, if you before we do anything, we check whether we are within a like-line certificate period. And if this is true, then essentially we have a loop where we obtain a commit. We verify using the trusted validator set if the commit is signed by more than 2/3 of voting power. Then we check whether the validator's hash is equal to our current validator set hash, because we set it to the next. Remember there that we said we were setting it to the next validator set hash. So now when we obtain the validator set hash from the next block, then this would be our actually what is written in our state. And then we compute from that header next validator set hash, like during initialization procedure. We check whether the validators corresponds to this hash, and then at this point we can install new set. And you see here also, like there, we set it to the kind of previous height and the time from the previous header, like from this point in time. So if we follow this, if you just follow the headers, we finally initialize the validator set, which will be in power for the height, which is provided as an input to this verify and update function. And so now, so this is like because Jack also asked, for having this kind of sequential specification, so we can implement this as this is simpler than the version with skips. Of course, we can be more clear here, and then we can try to jump ahead and not verify all headers. And this is more or less, this boils down to the spec Joseph wrote, which seems to be problematic from the implementation point of view. And so there we need to figure out if we can be more clever at the protocol level to let so it can be implemented efficiently. But so I haven't included that part yet, because idea was to try to cover the basics, and then this can be seen as an optimization, like performance optimization. Important one, but and it's also covered in the other spec.
Cool.
So think which was, I was having a bit trouble to figure out what we actually expect from the Tendermint RPCs. Because this is something where I'm not sure, so I was checking a bit code, and even now I'm not fully sure, because essentially when you ask for the validators for a given height, then do you obtain the state which is part of this kind of Tendermint state data structure, or something else? And
what do you mean?
So the kind of the problem I was having is the fact that as part of the blockchain, we don't have all those information written. And so you need to refer to this Tendermint intermediary state to kind of obtain information, if I'm not wrong.
Yeah, that's true. Well, okay, so it's true, but there's a caveat. The caveat is that, oh, interesting, never mind, no caveat. I was gonna say that the votes in the commit actually include the validator address. But currently if we didn't receive a vote from a validator, then we just leave it empty. And so, a commit that maybe has 2/3, but not everyone, will contain the address of everyone that voted, but doesn't contain addresses for people that didn't vote it. So it doesn't have the complete validator set.
Mm-hmm.
Of course, it doesn't contain the voting power. And in the upcoming change, to reduce the commit to just be signatures, we might keep the address in there as well, and even include it for the people that didn't vote, and then you would have a complete list of addresses in the block. So a complete list of validator set addresses in the block, but still you wouldn't have the voting power. And so whether we want to actually include the voting power, I guess, is a separate issue, possibly not. And then, yes, it's basically about syncing it's about the Tendermint state, which is this kind of object kept separately from the blockchain that can be recomputed from the blockchain, but isn't included in it directly, but commitments to it are. So, so the Tendermint would serve the validator set from the Tendermint state, and then you'd be able to verify it against the blockchain by taking the Merkle root.
This is something I was just, I was puzzling myself with, especially with this offset, that we have this next validator set is actually in power 2 blocks after, and then, it always kind of tricky to convince yourself whether you are calling validators for the right, height, or it should be +1 or +2 or whatever. So, but probably this should be kind of fine because the validator set, next validator set hash should correspond to what you get by calling validators for the height +1.
Right.
This is the only kind of assumption I was making here.
Yeah, that's right.
Okay, and so what is also not, what is kind of outside the scope of this version of spec is the fact that so how we are really submitting the proof of misbehavior, how we ensure that we can really obtain this, and so this involves some kind of redundancy in the in establishing connection not with a single guy but also with multiple guys. Potentially also changing this set from time to time with some kind of, ideally pseudo-random peer selection or secure random peer selection, and so that we somehow will have a chance to connect to a good guy. But they are very hard to specify, I think, from the kind of formal point of view. What should be done there so that you have kind of any guarantee.
The other thing that would be good to, so that's definitely something that has received insufficient attention, is exactly like, the kind of peer considerations for the Lite client. And so, there is at least one correct peer assumption somewhere.
It's everywhere, actually. Like
everywhere. It exists for the full nodes as well. That's right. Yeah.
So this is somehow we are assuming this implicitly, and there is some work which is done with a student of Fernando on trying to define some kind of ticketing mechanism which gives you a possibility to select the peers without knowing the overall peer set. But it's kind of still a very experimental thing, and we don't have anything like that, as part of our infrastructure. So I think right now we don't have any means to ensure that, if you connect to a random number of full nodes, one of them will be correct. So.
Right, and we don't have any kind of, the decision was made a long time ago for the Lite client to happen to engage through the RPC rather than through the peer-to-peer network, and so we don't currently have like a peer exchange protocol for the Lite client for it to actually discover new peers. So all of that is a little bit left unspecified, and it's probably something that should be addressed to actually round out all the concerns in this protocol, because ultimately it's going to kind of rest there. The other thing that would be good to address in the spec is exactly the kinds of Byzantine behavior that are required to be detected to mitigate, to ensure the security of the protocol. I believe that for the when you're verifying every header, I believe the only one we have to worry about is double signing. Yeah. But as we've discussed in the past, for the bisection or for skipping, at least 2 other kinds of evidence are required as well, that have to do with like signing either invalid blocks or signing blocks after you've unbonded. And I still there was a way to kind of write the formulation or to formalize the problem so that those would fall out somehow. The things you have to slash for would like somehow fall out of the formalization of the problem. That might be a little bit too optimistic of a goal, but that's really the dream for me.
Yeah. So I guess that we are more or less constrained here with the information we have available, and this is essentially pre-commit signatures. So you can detect equivocation, but also a fork, which is like equivocation, but kind of more frequent one. And I don't see obviously what else we could detect as a proof of music error if we have only access to pre-commits.
But when you say you can detect the fork, is it like, there are cases where I can detect it, or can I guarantee that?
So if you somehow connect to two nodes and one is giving you a commit for height h and the other node is giving you a commit for like different commit for the same height, then this is clearly fork.
But I must be lucky somehow, right? It's not something that I'm going to guarantee.
I mean, yeah, because there is no guarantee there, because you are maybe just talking with to faulty guys. They are trying to. I mean, it could even be that that the full node you connected to are also tricked the same way, because he is also eclipsed by a subset of nodes, and they created a fork, and you as a lifeline, you just discovered this by connecting to a full node.
Yeah. So that's the question, sort of, if we are we going to eventually be able to, I don't know, limit the duration of a fork somehow? And we somehow have the feeling that because if you're a light client and you cannot detect the fork, you might synchronize to something wrong. Yeah. And there's no way to prevent this because you cannot detect whether there's a fork. Right?
Yeah.
Is it acceptable?
No. Of course, this is the problem, right? And this goes back to the peer issue of like defining, what the connectivity should look like for the light client, so that before it goes too far in the syncing process, it tries to validate with multiple sources, so that it knows, or that at least someone's going to get punished for the fork.
Yeah, I think that my understanding is that we cannot prevent forks from happening. We can just incentivize nodes not to do it because we would be able to punish them. And so
that's right. We need the credibility of punishment needs to be high enough, right?
Exactly. And so like right now,
go ahead.
Yeah. So right now we have the only mechanism we have in place is the light line certificate period, which is smaller than unbonding period.
Right.
And so you are saying, okay, I will not talk with you if I pass half of unbonding period, because I'm entering the risky zone. So if you try to trick me, then you can do it only within the first half of unbonding period, and then in a second half I would maybe detect, because I'm talking with the multiple peers, so I might discover that you are bad, and then I will have enough time to submit this evidence and you will be punished.
Yeah.
So this is this is the first mechanism it seems we need to have in place. The second one is essentially changing periodically, probably also within the scope of this light line certificate period, that we are changing the peers or talking with multiple peers, hopefully selected by some kind of random function, and then we check the information we have.
Right.
But this is like I think that it's very hard to design something deterministic there. I think we need to we'll have some sort of probabilistic guarantees there.
Yeah.
That, like we sample the network from time to time, and we sample the state, and then if they don't match each other, then we have with some probability enough time to submit this to the network, hopefully through some, like direct channel, so we don't need to go through the mempool, to send such sensitive information. And then we can, push validators enough so they really include this is some of the next blocks. And hopefully this will be enough strong incentive for validators not to do it.
Yeah.
But I'm not sure that if we can do more than this. I would say no, but maybe I'm wrong.
I mean, you can imagine protocols where, we'd have to kind of probably implement these on chain somehow, but you can imagine additional protocols where people commit to providing like valid information for longer or something. And so it's like, a node puts up a bond that says, okay, I'm going to service like clients, and if I give incorrect information to a like client, my bond is slashable. They would like sign everything they would return to a like client. So the like client has evidence that's like, okay, I got this information from this node. He put up this kind of a bond. It's kind of rebuilding some of the proof of stake, the original proof of stake logic, kind of at another level, which might be, it's like turtles all the way down kind of issues, but those are kind of further off. And ideally, we can do as much as possible without going there, but those options are on the table later on.
Yeah.
But definitely the client, we have to figure out some way for the client to like sample the peer set and have a dynamic group of peers and change the peers it's talking to, or specify some trusted peer and calibrate that, or check that against others, or not totally straightforward. And the best we can do, like you said, is probably probabilistic guarantees.
Okay.
Cool.
So the question is like, what would be so I will create a PR with this, try also to take into account some of the feedback and comments, and then it would really cool if we review this, see if there are some issues, and then if once we sort of agree on this, the question is what would be the next step or next steps, because there are probably
there's probably a few. So there's both. So from an implementation perspective, it would be great to get the sequential verification implemented. I know there's ongoing work refactoring the light client package. I think that's still waiting on an ADR for clarity on the actual code architecture there, independent of all the protocol specification. So hopefully that comes into play, and then we can actually get a implementation of just the pure sequential, basically this specification. And then the next step also is to figure out how to do the skips efficiently, if that's even possible. So that the next step here might be for us to go through Joseph's write-up again and to really throw some brain power at the problem and see if there are, if there's a trick or somewhere we can be clever to actually reduce the complexity, because right now it seems like it's like exponential or something, if I recall. And I think Anka did some. Oh, Anka's not here. Oh, is she off today?
We had a meeting in the morning. I don't know.
I think she was having some appointment in the afternoon. I don't know whether.
That's right. Yeah, that's right. Tell me that.
So one thing about what we discussed then following the write-up was that perhaps it would help sort of to have additional information in the blockchain, like like the height when the last time the validator changed, set change.
Yeah, interesting.
This might be one thing that would help a lot in sort of jumping to the chain. I don't remember the details, but it was one.
I think that the problem Anka was raised by essentially really measuring this experimentally is the fact that we need to compute these potential adversaries, and they are like given a set of validators. Then these are kind of all combinations which create, I think, at most 1/3 of validator sets.
Right.
And so, like with 100 validators, this is already infeasible. So I think that this is like the fundamental problem. So we somehow need to try to achieve the same goal without computing potential adversary.
What about with oh, never mind. Yeah. Well, I'm wondering if given the incredibly lopsided nature of the distribution, I mean, we don't have 100 equally weighted validators, right?
Mm-hmm.
So I wonder if you can do the computation after chopping off, just take the top 20 validators or something, or top 30 and do it there. Because they have, right now it's like the top 16 validators control more than 2/3 of the network. So,
yeah, but this is the problem is that potential adversaries are actually all the small ones, and this is the problem. And there are much more than the big ones.
Two of the big ones and then all the small ones, and then you end up with more than 1/3.
Exactly, and that's the problem. And so it's really a lot of them. And so I think that we need to try to achieve the same thing without computing all potential adversary sets. So maybe.
So we actually, Joseph, do track the last height the validators changed, but not in the blockchain. We track this in the Tendermint state. So there isn't a commitment to it, but right now the way we store validator sets and historical validator sets is we only write the validator set to disk when it changes. And so we track the last time it changed, so that when you query for the validator set, it kind of does this more, somewhat optimized lookup where it says, okay, what's the last time it changed? And then, if it hasn't changed in a while, go look up whatever it was last. And so we don't store redundant information basically, but possibly we could include that in the block if that's something that would help. But it seems like we need a bit more brainstorming on exactly on this problem. And I don't think we were, when we talked about this, it was 2 months ago now or something. I don't think we recorded it. I'm not sure, but it might be worth an actual, Thursday dev session on it, just to make sure. And not everyone was there too, if I recall. It was kind of a different group. So it might be worth doing it again, maybe next week. Now that we have, this under the belt, and we've talked about this stuff a lot, we can really focus in on the issue there.
Yeah, I think this is a good idea. And so in the meantime, we can really try to figure out at least a few heuristics how we can, at least in some scenarios, detect and do the skip faster. Because we don't need...
Next week is a little bit complicated for me because I'm at a conference in New York, but the week after that would work. And the point, but I agree that, if the data is in Tendermint, then at least we should really think about whether it makes sense to get it into the blocks. We should understand whether this will help us.
Yeah. One also, what I was thinking a little bit is whether we can push this computation to validators, so that when there is a new validator set hash being installed, that it can somehow maybe do this check. But then we need to figure out then how we can then somehow benefit from this on the Liteline point of view.
Interesting.
So,
in principle, you could, the points to validate the potential adversaries, you could pre-compute them and write them there, but it's a lot of data, I guess. I don't know whether you want to put this into the...
It's more like I was thinking if sort of if we detect that we are in some of those lucky cases, that we can know this and then provide this information to the live client.
Right.
So we can do something like this.
Right.
Because there are some scenarios in which the computation is easy. We don't maybe even without computational potential adversary. So if we maybe record those things, then at least we have a kind of lucky path.
Right.
From the lifetime point of view.
I agree. If the changes in the validator set are rare, then sort of the lucky case that they are equal is already a good one, and we can have a pre-check, and we figure out what cheap checks, and then we can always fall back to the sequential thing.
But it's true that we haven't really thought a lot about what is really efficient way to implement this and what we can do at the Tendermint to maybe facilitate this. So we can maybe try to think about this in a following period of time, and then I think it's also a really good idea that we try now to have as many eyes on this as possible. So we really try to at least set up some base here so we can really start coding and unblock also ABC and all the stuff which are blocked on this.
The other thing we have to do as part of this is fix the BFT time to be proposer based, and so we'll have to resurrect a.
Yeah. So this is something which I think also it deserves dev session. I'm still not convinced that this is a very good idea.
Okay.
Because I thought that it's I convinced myself that we cannot avoid doing this, but the problem is that we are really changing the system model there. Yeah. Which means that essentially we need to write a new consensus protocol with all proofs and everything, and so this is a risk. And on the other side, there is also a high risk that if those assumptions we are making there does not hold for any reason, like for example we are attacked by a hacker who changed the local clock, we might be blocked for a quite long period of time. Yeah. And so this is a risk.
Like the current, we know that the current system also doesn't work for like clients or
no. So the alternative is so I think that I think what could be alternative is again that we try to stay closer to the current system where we essentially use median and then try to incentivize strongly validators of being close to the NTP time.
How?
And by introducing the punishment if we see that they are too far from the vault time.
How are you going to prove that?
But if the bound is like six hours or something like this, is pretty high. You can kind of prove this. You cannot prove.
But you can only prove that they are in the future, right? In the past, the message could always be slow or something.
But the past seems not to be a problem because we assume we assume monotonical increasing time, and so you always
the hybrid unbonding time might actually solve this for us, and then that's actually really interesting. That because just to kind of recap on the problem is right now with the way we do time, and so suppose the unbonding period is determined solely through time, not through block heights, right? Then the problem is that right now the way we do time, because we take the median of the timestamps, it means that a cabal of more than a third of the validators can arbitrarily move the time into the future. And so if they wanted to, they could fast forward, within a few blocks or even one block past the unbonding period, right? And then they'd be able to double sign without any consequence and they'd be able to do it very quickly, and they wouldn't be able to be punished on the blockchain because as far as the blockchain is concerned, 3 weeks have passed, even though according to wall time, it's only been an hour or whatever, right? And, you might say, oh, well, that's more than a third, so it's outside the security model, blah, blah, blah. Except the challenge is we tried to build Tendermint so that, even cabals of a third are always accountable. But the issue, so that, you have a cabal of a third and they double sign, whatever, at least you can still find out who was responsible and punish them. The challenge is they're just moving time forward. You don't have any like definitive canonical, global reliable time source to punish them against. You can't really detect that they fast forward this thing maliciously, right? And so basically it completely compromises the potential security of the light client for a third to be able to just fast forward the time and not get punished for it. But if it's based on height as well, if the unbonding period is a hybrid of time and height, then it would require that at least some number of blocks passes, even if they try to fast forward 3 weeks within 2 blocks, the unbonding period would still say, well, you also need 10,000 blocks or, whatever it is, 50,000 blocks. I don't know, probably like 210,000, whatever. That might actually help very significantly. Yeah. So, it's not a great solution, but it could be a stopgap.
Yeah, this is exactly what I was mentioning before, but probably I was not clear. Yeah. That essentially this is a way to solve the security point. At least security of the light client, but also security of the main chain, because the same problem you have there. It doesn't solve necessarily the problem of kind of reliable time source, because it can be manipulated if you have more than 1/3 of let's say misconfigured local clocks, because it could be also that it's correct guide, but it's attacked, or it's just broken source of time. So I think that's why I think that we need to be more careful to really define what are the goals, because the current version has a lot of benefits on the just aliveness of the network, and so we don't really rely on this thing. So the introducing NTP is a very strong dependency, and NTP is also a distributed system which can also be attacked. Although it's maybe the question is what are the probabilities, but I don't know how much we want really to rely on this system for.
Did you see? Did Libra have anything interesting on the time front?
I haven't seen anything about time there. This is like I try to sort of search this. I talk also with Joseph about this, but we are not familiar with any work which is kind of trying to combine the time as part of the protocol itself. So normally you rely on this kind of protocol to define the source of time, but not use NTP.
Exactly.
Yeah. So it's the other way around. Never seen. So that's why I think that maybe maybe it's still worth of trying to think about what alternative mechanisms, especially short term, because I think short term, like changing this proposer time, is really like a very, very major change, because it's essentially changing a protocol, and all security, all the things we did are kind of under high risk. So
no, I really didn't. I mean, that's why we haven't done it yet, because of how much it compromises like the liveness proofs and how hard it was to get a liveness proof in the first place. But the things, I mean, the other thing, so basically the two things it has going for it though are, one, it would require 2/3 to actually compromise the time, which is, that's where we want to be. So I don't know if there's another way to require 2/3, to have that kind of guarantee that it would take a 2/3 cabal to compromise the time without potentially sacrificing liveness. So that's kind of a interesting question I'll throw out there. If someone could come up with a mechanism that would do that, would be super interesting. The other thing though is from the perspective of, signature aggregation, it would be really nice to get the timestamps out of the signatures, out of the commits, right? Because otherwise we're going to have to, we won't be able to aggregate those timestamps unless, again, some brilliant cryptographer comes up with a way to do that kind of clever aggregation on the timestamps. But that seems possible. That seems like very, very difficult. But yeah,
I think that it's also, it makes sense to look at this proposer-based time. That this is definitely also a valid direction, but we just need to be careful to cover all to understand really well first whether we can do them and what would be the cost there, what are the risks, and also what are alternatives. Because the question is really, how we need also to play a bit game theory there and to see how reasonable it is to really do this kind of attack. What you would gain by significantly changing the clock. Because this is something, although it's not really, we don't have right now a mechanism to punish this. This is easily detectable. Like if you move the clock a few hours even ahead, then everyone can detect this. And so it can raise a concern. Yeah. And so if light client security is not affected by this, by having this hybrid clock, maybe we are good to go there. And now aggregation, signature aggregation, this is a different story. But I think also there, maybe, we need to think about
but
different mechanism to satisfy that requirement, but not necessarily.
But when you say it's easily detectable, this detection also rests on assumption about some synchronized clocks or something, right?
Yeah, I think that we should probably advocate all participants to use to rely on synchronous clocks. So light client security, as we discussed at the beginning, depends on this assumption. And so no matter whether we use a median-based time or the proposer-based time, we still need to use NTP. And light client will somehow depend on this. But this BFT time drift is somehow covered by the light client certificate period, largely. And so the question is, do we really need to define the BFT time drift bound? Because if we say the light client certificate period is half of the unbonding period, which is order of days, then this covers all kinds of clock drifts. Like otherwise, if your clock needs to be completely broken, and then if it's broken, we can maybe figure out some kind of at a user level, raise alarm and say, something is wrong there. Please go and fix your stuff. But this hopefully will not affect the chain, and it will not lead to the chain, halting. So my sort of suggestion is to try to address all those concerns carefully and hopefully maybe, thinking about them in isolation, because maybe we have a simpler and more secure way to deal with them and not have, one approach which will kind of try to resolve all of them.
Yeah, that's a good point.
Yeah, because aggregation also, maybe, we haven't also tried to just, take the timestamp out of signature. Maybe there is a way to do this which will not affect the correctness of protocol, but still lead to a possibility to aggregate signatures.
Yeah, maybe. Aggregation's a whole other story, and I think it's still kind of a big unknown in the aggregation thing about weighted aggregation.
Yeah. Also, I'm kind of wondering, because we have this proposer-based timestamp as it's planned for 33 release of Tendermint, and so I'm not sure if it's really a good idea. So maybe this is too. There's no way that we do this in a reasonably short time frame in a correct and reliable way to change complete protocol.
Listening to this conversation, it seems like we should move that out of 033 because it seems like there is still open discussion and both sides, there isn't consensus of going forward with it or not.
And so maybe, we can focus on what we can do. And so these lifeline stuff and maybe this kind of hybrid unbonding period is something which is much more reasonable. And we can do this and still have significant security as as a next version. So in general about light client, although I don't know how good is to reason in terms of like partial correctness, I really don't like this thing, but maybe we also don't need to have light client in a perfect form in a first version. This would be very hard. So maybe we should try to shoot something which is a bit simpler and still have reasonable security, and then evolve also the security of it over time as the system mature.
I definitely agree with you.
The only thing I'm looking out for is just packaging or bundling breaking changes, right? So if we're gonna make a breaking change to the header, I don't want to make one or to the block structure or something significant. I don't want to make one, soon and then another one a few months later. Once we get around to it, like ideally they would all come together, or at least there would be something like a 6 month. A 6 month break, a 6 month kind of stability guarantee on the protocol, on the block protocol, so that your blockchain will last with upgraded versions of Tendermints for say 6 months before there's a breaking change. So
and that goes back to what I brought up on Monday on LTS version. If we decide to do an LTS version, then I think it's better to go with an LTS version than focus with backward compatibility, because we do say in the README that this is alpha software. Expect breaking changes every release.
Totally. I mean, we say that, but the more we do that, the more upset our users are, and the more likely they'll try to abandon or something. I don't want to depend on like any kind of lock-in. So as much as possible, I'd like to respect some form of, we're still breaking RPC and whatever. And like, I'm less concerned with that because it's easy to just like update your software versus updating the whole blockchain, signed data structures. You can't just like fix those, So,
but maybe we can. One idea is to try to postpone this proposer-based time to push this a bit more ahead, because the other requirement, the aggregate signatures, is also pretty far ahead of us. Right now,
if we have a convincing security argument for how to deal with time for the light client without the proposer-based thing, then we can push it, 6 months, a year into the future until, right now the primary motivation for it was the security of the light client. But if we can address that concern, without changing the way we do the BFT time, that would be incredible. And then the motivating concern would be aggregate signatures, which isn't going to happen until 2020 anyway. So, So that's really, if the hybrid unbonding period is a solution, then that would be great.
Should we wait to kind of make the decision if we're going to pull that out of 033 or not, based on Zaki's ADR? He's writing up an ADR for the Lite client, and then we can see what's in there and then open discussions on that. And then kind of after we have consensus on the Lite client, how we move forward with it, then we decide on the proposer timestamp.
Sure. I think we need to collect more data, and we certainly need to figure out if if something like a hybrid unbonding period is sufficient for the security concerns. I'm not sure to what extent Zaki's ADR is going to address like specification level stuff versus just architectural, like code level stuff. So we'll have to kind of see. But it seems like the dev sessions for the next few weeks, and maybe we'll do them more than just once a week, just to kind of keep up the momentum, are going to be really focused on this Lite client and time stuff. So. Yeah, we'll keep iterating and discussing before we make final decisions. Yeah.
Okay.
Cool. All right. Anything else?
Yeah.
Do you have stuff related to the session, or should I stop the recording?
You can stop the recording.
Okay. Thank you, Zarko, for the presentation and for the great discussion, everyone. We will follow up in future sessions with more on the Lite client.